Very happy to welcome you all to this very special colloquium today. Special for many reasons. I think after 2 years we are meeting in person. Yeah. And I hope we can continue doing so. Rarely we have this many people in the past and so I hope that it ends. You may have been told by many people that you are not expected to follow all these phenomena, but even a major part of it. If you get something out of it, then it's certainly easier for another. So I am very grateful. I think that people to talk. Usually we have between 5 and 15 and it's very special for the reason that it's our own student, Naina, student for us, friends of some we have done this work in collaboration with some other students at fields institute, summer work. Usually student projects deal with something elementary mathematics, though there may be very difficult and clever algebra. More than one does not get. But the mathematics is usually at an elementary. These things have gone much beyond that. And I hope it will inspire others to mathematics. But Naina has been one of our industrious, hardworking, sincere students. And we are very happy that she has done some very good work. And as I told her, I also hope this will be the first of many things. Welcome.
Hi everyone, good evening. Am I audible to the end of the room? Okay. Am I audible right now?
Yeah.
Okay, cool. So, good evening everyone. Today I'll be talking about the restricted invertibility of continuous matrix functions. And so, restricted invertibility has to do with some basic properties of matrices. And so this was done jointly with Pan, Montemurro, Mutatis, Solis, Kuprenis, and Praveen. I think Alyssa is also on the call, so if I make any errors, please do let me know. All right. So, yeah. So to begin with, we'll start with what's called a linear function. So if we're given any two vector spaces over a field plane, we can define a linear map to be any map that basically preserves addition and scalar multiplication. So if you were to imagine this in say R2, it's sort of like you can either rotate the plane or stretch or do various kinds of things to the plane as long as you keep the origin in the same place. So for a visual representation, you can see this cool. One second. Yeah, this animation by 3-2-1-the, which is essentially what happened is that the vector, the grid that we had earlier kind of got rotated and stretched. And so you can kind of track where every vector goes, and you can represent this transformation in the form of a matrix. So initially you had the vectors 0, 1, and 1, 0. And now after you stretch this over, it goes to the vectors 3, 0, and 1, 2. And to sort of encode this transformation, you can represent it in the form of a matrix, which is given by 3, 1, 0, 2 out there. So whoever's taken a linear algebra course would know that you can represent every linear transformation in the form of a matrix, and vice versa, every matrix represents a sort of linear transformation. So if I were to generalize this in higher dimensions, then any n cross n matrix would represent a linear map from Rn to Rn. So one fundamental property that we can ask about matrices is whether they are invertible. So this is usually called either being non-singular or non-degenerate. And when we talk about them in terms of matrices, the usual definition that is given is that if there exists another matrix B, such that A times B gives us I, where I is the identity matrix, then the matrix is said to be invertible. What this means is that if I have a transformation, the question is, okay, can I kind of find an inverse map to go back to what I started with? And if you were to look at matrices in terms of linear maps, then all we say is, okay, as long as any non-zero vector is not taken to the zero vector, the kernel is trivial, then this map is invertible. So for example, the first map is a 3 cross 3 identity matrix. And what it does is in R3, it makes every vector just go to itself. And the second one is another kind of matrix, 1, 1, 1, which what it does is the span of this matrix has dimension 1. And so this matrix is not invertible because you do have non-zero vectors that do go to the kernel. So you can have another matrix like 0, 1, 0, 0, 0, 1, and 0, 0, 0. And what this does is it maps everything in the z-axis to the y-axis, everything in the y-axis to the x-axis, but everything along the x-axis kind of just goes to 0. So you kind of, there's some non-zero vector that's being taken to the kernel. And this is, again, not invertible matrix. Now, invertibility school, we would like to have invertible matrices, but unfortunately, as you can see, not every matrix is invertible. So this is another example of a, say, 5 cross 5 matrix. And so the last 4 columns of this matrix are linearly independent. And so as long as we don't have linearly dependent columns, our matrix is invertible. And so moving on, then we define this concept of a rank of a matrix. So the maximum number of columns that are linearly independent is what we define as the rank of a matrix. And in some sense, the rank of the matrix gives us an idea of the degeneracy of a matrix. You can kind of say how degenerate a matrix is based on the rank, because at least those columns are invertible. So for example, we can take the first matrix. Now this is a rank 1 matrix, and this is singular. But if we were to perturb this matrix a little bit, add some amount of noise, then this matrix becomes full rank. And so this matrix, in fact, has rank 3. Right. So we want to be able to see whether something is invertible. So in the first matrix, we realize that since the dimension of the span is only 1, there's a subspace of dimension 1 that's invertible. But since this is full rank, we can say that, you know, the whole space is invertible. But if you think about it, these matrices are really not like far apart. So even a little bit of noise, a little bit of perturbing can change the rank and the singularity very much. And so we would like to have a better notion to, you know, categorize this degeneracy of a matrix. So instead, what we do is we try to look at a different notion and see if we can categorize this invertibility better. Because for this matrix, even though it's so close to being singular, there are non-zero vectors that are very close to 0. And we wouldn't want that. That's very close to being degenerate. So in order to do this, we define another concept called the least singular value. So for any n cross n matrix, we define it to be the infimum of the unit ball after the transformation over the norm. So for the visual representation, if this went over your head, if we were to have a unit ball and we were to transform it, then it becomes some other shape after this transformation. And so then we look at what's the smallest that a vector has been stretched or shrunk, and that value gives us the least singular value. In this case, it's essentially just that the length of the red arrow out here. And from this, we can deduce that the norm of every vector after a transformation is at least sigma times its length. So what we're saying is that no vector is essentially shrunk beyond this least singular value for all the vectors in the space. So in this matrix, this is the identity matrix, the least singular value is 1. And so no vector essentially gets shrunk beyond its own size. In fact, everything just stays the same. In this matrix, because this is rank 1, there are vectors that in fact go to the 0 vector. So the least singular value for this would be 0, because you have some non-zero vectors who are basically just being, you know, shrunk to 0. For this matrix, the one that we perturb a little bit far away from the matrix A2, are very close to 0. So it's not necessarily 0 because this matrix is invertible, but it's very close to 0. So there are vectors that are very close to being brought to the null vector. So instead, what we do is we try to say, okay, we want to define another, like we want nice invertibility. We don't want this kind of invertibility where you're so close to 0. This doesn't serve our purpose. So instead, what we do is we define this notion of well invertible. And we say a matrix is called well invertible if its least singular value is bounded away from 0. So we can fix some constant, say C, and say that if my least singular value is bigger than this constant, then this matrix is well invertible. So if you don't want, say, vectors to shrink beyond some size, in the subspace are not shrunk below the size, we're good. This is a well invertible subspace. So for example, in the previous thing, if I were to set C to be 0.5, which is to say I don't want any of my vectors to be shrunk below half its size, then for this matrix, this very slightly perturbed matrix, we can see that the least singular value is 0.002 approximately. So this is to say that there is actually some vector that goes to almost 0.00 twice, 2 times its size. So it's really really close. So obviously this whole matrix cannot be well invertible. So like you would see that invertibility wise, this matrix has rank 3, but well invertible wise, it's not rank 3. Okay, so so now we have defined 3 singular values. We have some measure of the kind of invertibility we're looking for, but now we want to characterize this because rank was not something that was very helpful, because even a little bit of noise and it could completely change the dimension of what we're looking for. So in order to better characterize this invertibility, we will define a notion called the numerical rank, which we will come to. But before we go there, we'll have to define 2 other notions. The first of which is called the operator norm. So to clarify, norm of AX is the norm of a vector, and this is like an abusable notation, I suppose. And the norm of A is essentially the norm of the matrix. So we say the So superficially, this is very similar in definition to the least singular value, where instead you took the infimum over the supreme instead of the supreme one. So for visual purposes, again, if we were to look at the unit ball and then under the transformation, it becomes some other shape. So we look at the longest vector, and the length of this longest vector gives us the operator norm of the matrix. For those of you who know about singular values, this value is also equal to the. We have the 2 notions. Okay, no, one more. So the second notion that we need to define is that of the Frobenius norm. So this is possibly one of the most natural ways to define a norm of a matrix. So since a matrix is essentially a vector in Rn squared, you could just look at it as a vector in Rn squared and then just take the square root of the entries of the matrix squared. And so that's kind of how you also define the norm of vector in any Rn space. Equivalently, you can also define this as the square root of the sum of the squares of the singular values of the matrix. If anyone has done singular values, then you would know what singular values are. Or equivalently, you can also define it as the square root of the trace of A times A transpose, where A transpose is essentially the matrix A with its columns and rows switched. Okay, so now we have all we need to define this notion called the numerical rank or the stable rank. So essentially, the stable rank is defined to be this fraction, the Frobenius norm squared by the operator norm squared. And this is essentially in terms of singular values, you can sort of do the math and realize that the value that the stable rank takes is always going to be lesser than the rank of the matrix, right? And so now we have all we need to define invertibility in the better notion that we have. So this question was asked by Burgain and Zafriri in 1987, and they said, okay, we want to find subspaces of a matrix that are well invertible. And how do we do that using the characterization of stable rank or numerical rank? And so they proved the following theorem. The reason they did this was for some question in functional analysis in geometry. I'll come to the history later. But what they proved is the following. So they said that we can find constants P0 and D0 such that for every matrix A, with the column norms to be 1, we can find a subset from 1 to n. So 1 to n is essentially a sort of indexing for our columns, and we can find a subset of these columns with the following property, which is 1, the cardinality of the subset. So the number of columns that we can choose is some constant times the stable rank. And for all the columns within this indexing subset that we have, the space is well invertible. So to repeat, what they said is we can find constant C naught and D naught. And we say that as long as our matrix satisfies the hypotheses that the columns have norm 1, the number of columns that we can find that are well invertible is bounded below by some constant times the stable rank. So this is what they proved in 87. And then they further improved the constants and they parameterized it. Oh, sorry. So essentially what we're saying is sigma is going to be some columns from 1 to n. So it's going to pick up some numbers between 1 to n. And then we look at the standard basis of corresponding to those columns. And so when we look at A times EI of those columns, we essentially get the columns of the matrix. Yeah. Is the space spanned by EJ?
Space span.
Yes. The Langle is the span. So we look at the space span. All right. So they further improved these results in 1991 and they parameterized it in terms of epsilon. So there's a sort of quadratic dependence between C naught and D naught, where if you take C naught, then D naught can be found to be some other universal constant D prime times 1 minus epsilon squared. So essentially what they're saying is, okay, if I want to get a larger sized, larger number of columns, then I can take epsilon to be small. And if I want to take a more better well invertible space, then I can take epsilon to be larger. So the reason they did this was they were working in some problem in geometry and function analysis, basically the Cadison-Singer conjecture. And for that, it essentially talks about some, I don't know very much about it, but it's something to do with certain linear functionals or certain C-star algebras, and if they're unique or something. And so this question was in fact solved by Nikhil Srivastava, Daniel Spielman, and Adam Marcus in 2013, for which they received the Polya Prize. And this statement by Bruggen in the field was extended to rectangular matrices by Verschain in 2001. And it's been further generalized and deproved because it's sort of equivalent to the Cadison-Singer conjecture. And yeah.
Can you please go back to the previous?
Yes, yes. Any questions?
No, I just want to understand that.
Okay. Essentially, we can just say that we can characterize the size of the number of columns with the stable rank, and we can make sure that everything within this is well invertible.
Okay.
Right. So the proof of this actually relies on certain probabilistic techniques. And I think that is kind of the key to their proof. So I don't know how they came up. So, okay. So the proof is fairly complicated and they've broken it down into lemmas. And this is sort of the first lemma in their proof, which I shall explain. And so it says that essentially the first two sentences say that if I have a matrix that satisfies the hypotheses of the Bruggen-Zeffiri theorem, which is that all the columns have norm 1, then I can find a subset sigma 1 of 1 to n, such that its size is again some other constant times the stable rank. Then this weird looking function norm is 1 by root. So what this is this is the projection of some columns on another subspace. So for example, if I had my columns to be 1, 2, 3, 4, and say sigma 1 was the columns 1 and 2, and 1, 2, 3, say. So then what it says is, if I were to look at the projection of the column of 1 on the subspace spanned by the columns by 2 and 3, then the norm of this would be bounded by 1 by root. And similarly, if I were to take the second column and I were to project it onto the subspace spanned by the first and the third column, then that also has norm less than 1 by root 2. And similarly, if I were to take the third vector and span it on the subspace spanned by 1 and 2, its norm would be less than 1 by root 2. And so this function is sort of magical in the sense that it's because of this function, the rest of the proof follows. And so what they do is they sort of pick a collection of independent random variables, indicator random variables, and they use the Bernstein's inequality to sort of say that with almost sure with probability 1, we can find such a subset where this function holds. And so this function sort of what allows us to guarantee the rest of the proof, for which they use like other probabilistic and combinatorial techniques to prove. So I think the sort of magic was the fact that they introduced randomness in picking these columns. All right. So this problem is also equivalent to another problem in functional analysis. So for that, to understand that second problem, we will define something called the C-factor of a matrix. So an M cross N matrix is said to be a C-factor for an N cross N matrix B if I can find two other matrices L and R, so that I can write B as L times A times R. And the norms of L and R are bound, the product of the norms of L and R are bounded by C. So this is just a definition. And so the question is, okay, can I find a factorization of the identity matrix? So if I were to replace B with the identity matrix, then can I still find such a factorization of the identity matrix? And so what this says is that if I have a matrix A with columns A1, A2 to AN, and the norm of A is bounded by 1, is smaller than 1, such that each column has a norm bigger than theta, then I can say that A is a C1 by theta factor of the identity matrix M, where M is bounded by C, some other constant times theta squared M, where C1 and C2 are some constant. So what they're saying is, okay, if I'm given a matrix with norm less than 1, with each column bigger than theta, then I can factorize the identity matrix, and the maximum dimension up to which I can factorize this identity matrix, the largest M that I can get, is bounded above by C2 theta squared M. And so this is sort of like an equivalence. So just a rough sketch to show how the Bruggen-Zeffredi proof, the theorem, restricted invertibility theorem, would imply this. And so we can look at T, the matrix defined as A, so the original matrix that we had in this theorem A. So we can define T to be A times 1 by the norm of each column. So essentially T kind of just normalizes every column in the matrix A. And then this matrix T satisfies the hypotheses for Bruggen and Zeffredi. So in this matrix T, every column has norm 1, which is what the Bruggen-Zeffredi theorem required us to have. And then using Bruggen and Zeffredi, we can conclude that we can find a subset sigma of 1 to n. Basically, we can find columns of this matrix T, which is well invertible, and the lowest number of such matrices that we can find is bounded by P naught and norm T squared, which is just basically the Bruggen-Zeffredi, and then that constant is C2 times theta squared m. This requires some work, but this is what you can show. And on that space, this matrix is well invertible. This is also what the Bruggen-Zeffredi theorem says. And then to explicitly calculate L and R, you can just pick some m number from the subset sigma, and then define R to be those standard B6 divided by the norms of. And you get L times A times R equals the identity matrix. So in some ways, the Bruggen-Zeffredi proof also solves the C-factor matrix question out here. Okay, so now we want to extend. So this was all history. Oh, by the way, so the Bruggen-Zeffredi proof is not constructive in the sense it just tells you that there exists such columns. It doesn't tell you how to find these columns. So it's not constructive, but I think in 2008, Trop defined like a randomized algorithm to compute these columns. Like you can explicitly find these columns. Okay. So now we want to extend Bruggen-Zeffredi's theorem to a continuous case, which means we need to translate everything into a continuous case. So instead of looking at matrices, we look at continuous matrix functions. Instead of looking at columns, we will look at a continuous choice of subspaces, right? So the first definition that we have in order to reach our continuous version of the Bruggen-Zeffredi is a matrix function. So what we do is we say we take an interval in R and we define a continuous matrix function to be any function from I into n cross m matrices over R. So for example, we can take this matrix, which is defined from 0, 1 to a 3 cross 3 matrix as a function of t. And this is continuous. And what it essentially does is basically as t varies, this projection, so the subspace on which this is being projected changes as a function of t. And what it does is it just projects every vector onto this changing subspace. So the red vector just basically gets projected onto this green subspace as t varies. So this is just an example of a continuous matrix function. And so now we will proceed to define continuous subspaces and bases. So we define a continuous subspace in the following manner. And so what we say is, okay, we have an interval of R and we have a family of subspaces indexed over this interval. And then this is continuous if I were to take the projection, orthogonal projection of every vector onto this subspace UT, and then the projection map is continuous. So Mn cross n is essentially giving me the projection onto every U of t. And as long as this projection map is continuous, the choice of subspace is continuous. And similarly, we can define a continuous choice of bases. So if we have m functions from I to Rn, gamma 1, gamma 2 to gamma n, and each of these are continuous, so that at each point, they also form a basis for the collection of subspaces U of t, then this is a continuous choice of bases. And you can show that this continuous choice of bases is equivalent to having a continuous choice of subspaces and vice versa. So they're both the sort of equivalent.
Assuming all UT have the same dimension.
Yes, yes, yes.
Are they taken that subspace also?
Yeah. So this is the choice of subspaces is changing, and we see that this family of subspaces. Yes. Yes. Okay. So now we want to extend. So now that we have the notion of matrix in the continuous case, we also have an extension of the choice of columns. So the subspaces in a continuous case, we are now ready to define the restricted invertibility theorem for continuous matrix functions. So what the theorem says is, okay, if A is a continuous matrix function into n cross n matrices, satisfying the property. So this is the same as the Brigance-3D property, which is that at every point t, the matrix columns, each matrix column has norm 1. Then we define lambda to be the supremum of the norm. So in that case, we had just the norm of the operator, but because this is the norm will also change as t changes, we take the supremum, and this, by the way, is bounded by root n because we restrict the columns to have norm 1. Then if you define lambda to be the supremum over the operator norm, and we define gamma as 0, 1, we'll come to that bit later, then we can say that we can find an n-dimensional choice of continuous subspace, where n is greater than d naught n lambda squared. So this is the same analogous to the Brigance-3D theorem, where we had some constant times n by the stable lamp, and some constant times the stable lamp. So this is the same thing here, just that instead of the operator now, we have the supremum. And so this family of subspaces that we can find is bounded below by this constant times n by lambda squared. And so that for every at every point t, every vector in that subspace is well invertible. And so the gamma comes in to say that we can get arbitrarily close to C naught as we like. So you can find a sequence that goes to C naught, so we can get as close as we want to being well invertible. So the projection map onto every subspace is continuous. All right. So in order to sort of come up with, okay, so say the most normal way that one would think of extending this theorem in the continuous case would be to say, okay, how about we just apply Brigance-3D pointwise? You know, we get some subspace at this one point, we get another subspace at this one point that satisfies the well invertibility property, and then we should be able to sort of, stitch them together and come up with a whole continuous choice of subspace. But the problem that happens is, okay, we need to make sure, one, that in this transition space, the well invertibility property still holds. And the second thing we need to ensure is that the dimension doesn't get lost. It's not like some vectors are passing through the null vector and then comes back again to the next one. So we need to make sure that these two problems don't occur when we are transitioning between the two. So in order to overcome that, what we figured was that if we have two disjoint subspaces, then we can sort of continuously travel between them using a sort of convex combination. It's not exactly a convex combination because you raise it to square root. But yeah, so you can traverse between the two of them without really losing anything in the dimension. So as long as they're disjoint, there's no loss in dimension. So this is just what we call a quadratic convex combination. And the idea is we want to use this to sort of stitch our subspaces together. So the proof of the theorem that we had has two proofs. One is sort of the naive approach, which you would use, which is like, okay, let's kind of modify the Boolean theory, apply pointwise, and see if the result still holds. And so that one, okay. And so the second approach sort of relies on just orthogonality and nothing as complex as the Boolean theory. And so, okay, so basically, I don't know why I have this animation, but if you want to go from U0 to U1 and U1 to U2, each of these subspaces U0, U1, and U2 are obtained from Boolean in the 3D, being applied at the points T0, T1, and T2. We sort of want to go from one space to the other. The idea is we want disjoint subspaces because our quadratic combination sort of only works for disjoint subspaces, right? So we want to say, okay, I have some subspace U0 there, some subspace U0 U1 here, and I want them to be disjoint, but they may be disjoint, they may not be disjoint, right? And so what we do is, okay, we say we can modify the Boolean theorem. We say that in the old case, we would have some, say, the U0 had some columns that Boolean that satisfy well in invertibility, and U1 also had some columns, and maybe there are some columns that are common between them, and we don't want that. So we modified the Boolean theory proof, and we said that, okay, even if I block off some columns of the matrix, I can still find a large enough subset of columns with the rest of the columns that are still well invertible. And so this sort of relies on kind of using this modified Boolean theory proof 2 times. And so because we're applying this iterative Boolean theory proof, the original one, like 2 times, yes.
So for disjoint spaces, I mean, you need to have some restriction on the dimension, right?
Yes, yes. So there is a dimensional, like in the theorem we use Invertible. Like that was just the definition of quadratic, but here we will look. So the theorem says that, so I haven't put the theorem because it's very messy, but we say that, okay, as long as I'm not cutting off so many columns, I can still find a large number. Yeah, so this thing basically allows us to sort of iteratively apply this modified Boolean theory. But because we're applying it iteratively, what happens is we end up facing we sort of compromise on the dimensional estimate. So in the original Boolean theory, we had lambda squared, but because we're applying it twice, we end up getting lambda to the power 4, which is not optimal anymore. So to sort of overcome that was why we came up with the second proof. So in the first proof, essentially, as I said, what we've just done was we said that, okay, we block off some columns. As long as we're not blocking too many columns, we can still find enough number of columns where well invertibility holds. And we can sort of stitch them together using this quadratic convex combination. The second proof is, so we realized that the reason we were facing this problem was because columns, this space spanned by columns are very rigid objects. They're like, they don't allow us to do very much. We're kind of forced to stick to only those columns of the matrix. So if we let loose a little bit and we say, okay, as long as I just have m-dimensional subspaces, can the theorem still hold? So I'm no longer looking at spaces spanned by the columns of the matrix. I say, okay, I just want any m-dimensional space. Can I still find a subspace where the well invertibility holds? And so we did that in the following way. So in order to do that, so this was the optimal bound using the second proof, where the constant then just became squares, which is optimal. Right. So what we did in order to do that was we used this cute small lemma that kind of makes the whole process easy. And what the small lemma says is if I have 2 subspaces, x and y, of the same dimension, then I can find an orthonormal basis for x and an orthonormal basis for y, where both x and y, xi and yj for I not equal to j are orthogonal to each other. So as long as the i's are the same, they're not orthogonal. But if they're different, then even between x and y, they're orthogonal. Of course, they're orthogonal amongst themselves because they're orthonormal, but even between the two spaces, they're orthogonal. And this can be proved. So I quickly answer the proof. But what we do is we say, okay, so we can define a projection map from Rn to the subspace Y. And if we were to restrict our projection map onto X, then we can define another linear transformation P transpose P tilde. And then P transpose P happens to be symmetric, so we can apply the spectral theorem. And we can sort of get an eigenbasis for that. And then because we kind of chosen an eigenbasis, we can sort of then set yi to be the image of the projection. And we can show that as long as it's not in the kernel, these vectors are orthogonal to each other. We can normalize it and then show that they're orthogonal. And for the rest of the space, we can extend it linearly and show that because any subspace is the direct sum of the subspace and its orthogonal projection, we can sort of uniquely define these vectors, and then those vectors are also orthogonal. So this is sort of something that someone may have done in a second course of linear algebra, and at least the information you need to do it, it's not trivial. But yeah, so the main reason for proving this lemma is it allows us to do two things. It allows us to kind of, so if I were to be given two subspaces X and Y, what we wanted was we wanted to go to orthogonal, we wanted to go to disjoint subspaces, right? Because we wanted to apply the quadratic convex combination. So what this lemma allows us to do is I can go to a subspace X tilde and X and a subspace Y tilde and Y of half the dimension. So not cutting down on too much. I still have a lower one. I know that at least n by 2 of them are there. Such that both of them are disjoint. Both of them are orthogonal to each other. And the second thing that it allows us to do is that we can now apply the quadratic convex combination and not lose out on any, there's no reduction in dimensionality. Like I still, so if I had m spaces, then I can just apply the quadratic convex combination to these x by tilde and x tilde, and I still have the same dimension. So I don't lose out on dimension. So this is what that small lemma allows us to do. And then this is now sort of, okay, no, never mind, not straightforward. But what we do is we say, okay, so this is sort of a very complicated diagram, and I will explain it. So the first thing that we do is we say, okay, we have a matrix function. We look at it in a compact interval in R, right? And so because it's a continuous function in a bounded interval, we can use uniform continuity to find out points in the space where well invertibility holds in some neighborhood of these points. So we can choose the neighborhood. So we can find a sequence of points T0, T1, T2, and so on in say the interval -1 to 1, where between the interval T1 to T-1, the matrix AT0 is well invertible. And so similarly at T1, I can find some matrix, the matrix AT1 between the interval T0 to T2 is again well invertible. And then similarly at T2, I can find the matrix AT2, which is well invertible in the interval T1 to T3. And so using uniform continuity, I can essentially partition my interval into these points where in small intervals, my matrices are well invertible. And now we say, okay, so now what we do is we apply the original Burgenser-Freely. So we apply the original Burgenser-Freely theorems at the points T0, T1, T2, and we obtain subspaces of some bound. And then of some size that's already given by the bound and some constant time to say that. And so now that we obtain these subspaces, we can apply the lemma that we had, just the previous lemma that I showed. And what this allowed us to do was to pass into subspaces that are orthogonal, right? So we can pass into subspaces of U0, U1, and U2 called U0 tilde R and U0 L, and then U1 tilde L and U1 tilde R, and then U0, U tilde 2L and U tilde 2R, the two stop subspaces. And now we can, since they're orthogonal, we can sort of stitch them together. So what we do is we say, okay, so I'm slipping some technical details into the rug, but what we can do is we can say, okay, let's pick a point S1 between T0 and T1. So the U0 tildes work, or rather satisfy well invertibility between the interval T1 to T-1. So as long as I'm within this interval and I'm on this subspace, I'm good. I have well invertibility. And likewise here, for U1 tilde L and U1 tilde R, I'm satisfying well invertibility between the intervals T0 to T2. So I sort of want to switch between the two of them. And in order to switch was why I kind of split them into two orthogonal spaces. And then I say, okay, between T0 to some neighborhood in the center, this curve around S1, I can work with the subspace U0 tilde L. Then on the interval around S1, I can sort of switch to U1 tilde R, and it works out there because both the subspaces satisfy well invertibility in that common interval. And I can, since they're disjoint, I can sort of use the quadratic convex combination to switch between the two. And now I have U1. So now for the rest of the space, I could just use U1 tilde R and be fine. But because we kind of want to iteratively apply this on this side, and there's no reason to suppose that between these two spaces, I would again have well invertibility. So I just say, okay, I just kind of work within the same subspace, and I kind of switch between U1 tilde R to U1 tilde L in this small interval. So I can again begin with U1 tilde L on for the next part of the interval. So it kind of just allows me to switch between the two subspaces because there's no reason to suppose that U1 tilde L and U1 tilde R would be the same. So it's sort of just a technicality that, okay, just before a little bit before T1, we can still switch between the same subspaces because obviously they're both subspaces where well invertibility holds at a point. So essentially what we do is we just use that lemma and we split it into two and then we sort of stitch them together in the right way. So that's sort of an outline of the proof that we had. And so then further direction that we could approach this problem is by looking at, say, Rn. So we just had one variable. What if we have, say, multiple variables? We want to look at maybe how the matrix changes along a circle or something. Then does the theorem still hold? Can we still find n-dimensional subspaces? And another question we could probably look at is, okay, what if I replace the Euclidean norm with some other P norm? Then does the conjecture still hold? So yeah, that's sort of what we did. Video animation credits for the first one to 3 blue, 1 brown. And yeah, any questions?
Anybody have any questions?
So for the norm case, you are just going to take the ratio of
Yeah.
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 And this, would you please give some intuition why the quadratic convex combination is used?
So essentially, you want to pass to two sub. Wait, what exactly do you want the intuition for?
Like why linear does not work, why quadratic, why not some other form?
Yeah, that's simply because we want to maintain the norm to be 1. And so uske liye we will take square root of the sum of the entries. And because we want the convex combination to sum up to 1, we take square root because we are squaring the term. So square root and square just cancels to become 1. So the norm of the vector still remains 1.
Yeah. I had this question. I don't know if you can.
Yes.
Yeah. So in the last slide, when you said P norm, maybe there was this question already. I couldn't hear clearly. Is this the periodic norm or?
Oh, not periodic norm, like the P norm, the Shatton P norm.
Right. Yeah. Okay. So then what about the periodic norm?
I don't know. Maybe.
Okay. Anyway, nice talking.
Yeah.
I don't know if you have. Yeah, I don't know enough about periodic analysis to make it.
There's topology, so can frame similar questions, I guess.
Alyssa, by the way, is one of the other collaborators. She also worked with me on the paper. So, yeah. Any questions, anything? Yes. Yeah. Yeah, very, very large. Because by the time the constants become like very. I'm not entirely aware of that. I suppose it's just very, very large. I don't really know if there's a. No. The constants are pretty sad. I think it's like some order of magnitude 10 to the minus 2. Something. So it's pretty bad. Okay.
One comment may not be complicated, but people working in random matrix theory, they generally consider IID random variables as matrices. So, I mean, earlier you were saying that because of small part addition, so singular value given is too much. So one thing would be useful to look at. So when you are randomly parted, then what kind of condition you can give so that you have sort of regularity in the behavior of singular value.
Yeah. I guess. Yeah. Thank you to whoever is online.
How did you come to choose such a problem?
So I think my supervisor was working in functional analysis, and he kind of sort of came up with the C factor problem. And he did something with another bunch of undergraduates in some previous year. And when they submitted that, so they didn't have an optimal dimensional estimate. And when they submitted for peer review, I think the referee or whatever said that, hey, you can look at the Brilliance-Freely theorem, but I suppose it's equivalent. And so then he said, okay, let's try this version out. And so I think with us, it was like, this is another problem we could approach. Like,